For 3.5, we have the exponential and logarithmic models, and we want to be aware of the graphs. So in the graph number 1, we have exponential growth. Remember that the horizontal asymptote will be at y equals 0, 0, comma 1 is the y-intercept. That's a picture you should have, kind of one of your basic functions that you have in your head. You also have the exponential decay, which is just a reflection over the y-axis. As far as the Gaussian and logistic models go, I would say just be aware of them. Know how to solve for maybe x in both cases. You can see those examples on the 3.5 worksheet. There are a couple of examples there. You would be responsible for those on the exam, how to solve for x. And then the last one is the logarithmic model. And remember, it looks like when you graph it on the calculator that it stops, but this thing will continue down along the vertical asymptote and then out to the right here. So it will have the inverse relationship here, so 1 comma 0, and then it will have a vertical asymptote at x equals 0. So that's basically what you want to do for those two examples. All right, the population of a large city can be modeled by the 1.8 e to the 0.026x power in millions, where x sub 0 corresponds to 1990. And what year is the population of the city expected to reach 2.5 million? So I would set my equation equal to 2.5 million and in this case my variable is up in the exponent, so I would apply a logarithm on both sides. Excuse me. First thing we always need to do is get the base by itself. Sorry. So in doing that, 2.5 divided by 1.8 is not such a nice number, so I'm just going to leave it 2.5 divided by 1.8 e to the 0.026x power. At this point now, we can go ahead and apply a logarithm, and I'm going to choose the logarithm that has the same base as my exponential. So really, they undo each other, so we can get rid of that, and we have 0.026x. And some of you may have already done this on your calculator, but I'm just going to leave it 2.5 divided by 1.8. And so then our last step is to go ahead and divide by the 0.026. And so when you do this, the x value turns out to be about 12.6 years. And so this is about 2003, let's say. So from 1990 plus 12.6 would put us sometime in, I guess in 2002, we'll call it, sometime during 2002. On this problem, I like to draw a timeline. And so this is the 0 mark. They introduced the bacteria at the start. After 2 hours, they know that the population was 256. And then 5 hours after that, so that would put us at 7 hours, we're at 541. And then at the 24-hour mark is what we're trying to find. So what I would do is first we got to find how fast or what is the growth rate for this particular culture. So if I start with 256 and it grows to 541, I can use the e to the r, and that was 5 hours long. So really the only thing I'm missing is that r value. So we're going to do the same work we did before. I want you to divide by the 256. That gets the base e all by itself. 541 divided by 256. You can go ahead and write the decimal in if you want. It's 2.11. I would keep the decimal on your calculator, but then you get ln both sides. Again, that undoes the exponential. So we have the ln of 2.11 is equal to r times 5. And the last step is to divide by 5. So right here is the r value. So you'd want to take that and go ahead and ln, your decimal, and divide by 5, and you should be getting an r value that's really close to 0.1496. But the real question in this problem is to figure out what x is, and so that's the population at the 24-hour mark. So let's just go from the 7-hour mark to the 24-hour mark. So that's 541 e to the r times 17 hours. It's only 17 hours. So then what you want to do is take your r value from down here and just put it right there. And so it becomes, just type it into your graphing calculator, do your 541. I like to hit second ln because it gives me the e and the exponent. Then you do your, I do second negative to punch in my last decimal, so I'll take that 0.1496483669 that I have on my calculator times 17, and we come up with something right around 6,887.